For decades, scientists believed the universe followed clear, predictable limits. But deep within astronomical data, they began finding corrections, inconsistencies, and measurements that simply refused to line up with existing physics. All of it led back to a single, extreme object. And in this video, you'll see how those corrected numbers and revised calculations exposed unsettling gaps in our understanding of black holes, cosmic growth, and the early universe, forcing astrophysics to rethink what is truly possible at the largest scales of reality. Astronomers used to think black holes grew like disciplined students of physics, following a strict curriculum written by gravity, time, and available matter. In that picture, growth is an effort problem. A black hole can only gain mass if something falls in, and even then radiation from the hot infalling gas pushes back, limiting how quickly the feeding can continue. The universe, in other words, sets a speed limit. If you know the age of the cosmos at a given era, and you know that limit, you can sketch a reasonable boundary for how massive any black hole should be by then. That expectation shaped decades of cosmology. Black holes were sorted into familiar categories: stellar mass black holes, born from collapsing stars; supermassive black holes anchored in galaxy centers, built up through mergers and long, patient accretion. The rules might be complex, but the idea felt stable. There was always enough time to explain the biggest objects, as long as the universe was old enough and the feeding was not too extreme. Then came the payoff, and it landed like a quiet contradiction. TON 618 is not just large. It is one of the most massive black holes ever measured, with an estimated mass on the order of tens of billions of suns. It sits in the heart of an extraordinarily luminous quasar, a beacon powered by matter falling toward an event horizon. By itself, that sounds like a familiar story, until the numbers are placed on the timeline. When astronomers translate its distance into cosmic age, it appears at an era when the universe had far less time to build something so enormous. Now, the growth rules start to wobble. If TON 618 began as a typical seed black hole, something like the remnant of a first-generation star, the equations describing steady, physically limited accretion strain to reach its mass in time push the feeding rate higher, and the outward pressure from radiation should choke it, allow constant maximum feeding, and the schedule still feels impossibly tight. This is where growth rate equations fail in practice, not because the mathematics is wrong, but because the assumptions behind the neat curve collapse when confronted with an object that seems to have sprinted through a marathon. And it does not fit comfortably into normal black hole categories. It lies beyond the scale of most supermassive black holes, edging into what is sometimes called the ultramassive regime, a label that signals uncertainty more than confidence. What does it mean when an object refuses to stay inside the bins used to keep the universe organized? That single question forced scientists to rethink black hole limits. If TON 618 exists, then either black holes can grow faster than the standard picture allows, or they can start far bigger than expected, or the early universe offered unusual conditions: dense gas flows, rapid mergers, or direct collapse pathways that bypass the slow climb entirely. It may represent a formation path that standard cosmology does not yet describe cleanly. Its existence alone creates unresolved contradictions. How can something so massive appear so early? What was the seed? What was the fuel? And if the universe built this one, how many others are hiding just beyond our ability to see them? Because if TON 618 is real, the next part of this story is unavoidable. The problem is not only one black hole. The problem is what it suggests about the early cosmos itself, and whether our picture of what is truly possible has been incomplete all along. The scale problem with TON 618 becomes even stranger when it is compared to the larger structures astronomers thought they understood. For a long time, galaxies were treated as the heavyweight champions of gravity. They are not just collections of stars. They are gravitational systems with dark matter, halos, vast reservoirs of gas, and orbits that can take hundreds of millions of years to complete. So the effort of modern astronomy became learning to measure galactic mass accurately, counting starlight, mapping rotation, and estimating how much invisible matter must be present to hold everything together. The assumption underneath all of that work was simple. Whatever sits at a galaxy center should be huge, but still small compared to the galaxy that hosts it. Then the payoff arrives, and it feels almost disrespectful to that entire hierarchy. TON 618 is estimated at roughly 66 billion solar masses, meaning its mass is comparable to tens of billions of suns packed into a region smaller than a solar system on cosmic terms. That number is so large that it invites a question that sounds like science fiction, but is not. What if the mass at the centre is no longer a minor component of the system, but something that rivals or outweighs what we usually think of as the main event? Now the deeper facts begin to rearrange familiar comparisons. The Milky Way contains on the order of hundreds of billions of stars, but the Sun-like stars that dominate by number do not dominate by mass. When astronomers add up the total stellar mass of many galaxies, the final value can fall below the 66 billion solar masses attributed to this single black hole. In other words, there are real galaxies for which the entire combined mass in stars is less than what this one object contains. Even when compared to typical galactic center black holes, TON 618 is not just larger, it is separated by orders of magnitude. The supermassive black hole at the center of the Milky Way, Sagittarius A star, is about 4 million solar masses. Put next to 66 billion, the difference is not a gap, it is a canyon. Sagittarius A star looks like a seed beside a mountain. This is why TON 618 does not merely stretch the upper boundary, it forces a new boundary to be drawn. Astronomers began using the term ultramassive black hole because supermassive no longer felt descriptive enough, and the uncomfortable detail is that only a few objects are confidently placed in this category, partly because it is rare, and partly because confirming such extreme masses is difficult at enormous distances. But if the estimate is even approximately correct, the implications are immediate. A mass like this dominates its region gravitationally. It does not just sit inside a cosmic neighborhood, it shapes that neighborhood. Matter does not merely drift toward it. Trajectories bend, gas flows reorganize, and the surrounding space-time is distorted on extreme scales. So here is the question that quietly follows from part 1. If a black hole can become this massive, it is not only breaking growth rules, it is threatening the old assumption that galaxies are the main gravitational units of the universe. And that raises an even sharper mystery. What kind of environment can feed a thing that heavy? And what happens to everything that tries to live near it? Astronomers did not just think black holes were extreme, they thought they were compact in the most literal sense of the word. A black hole could have an enormous mass, yes, but it would still be packed into a boundary so tight that the mind naturally imagines a small dark sphere, like a cosmic pinprick. The effort for decades was learning to hold two ideas at once: immense gravity and a surprisingly tiny footprint. That is why the phrase event horizon feels so sharp. It sounds like an edge you could draw with a pencil. Then TON 618 shifts the scale again, and the payoff is almost unsettling. This is a black hole whose size is not described in kilometers in any intuitive way. Its event horizon spans multiple light days. In fact, light would take about 7 days to cross the width of its shadow. Pause on that. 7 days, at the fastest speed the universe allows, just to move from one side of the darkness to the other. Now compare that to something familiar. Light crosses the sun in only about 5 seconds. The contrast is not merely dramatic, it changes what the word compact can even mean. And the deeper facts make the weirdness more physical. If the size of a black hole is tied directly to its mass, then TON 618 is not an exception. It is the rule taken to an extreme. As mass rises, the event horizon grows. That means this horizon can dwarf planetary orbits. It is not simply larger than a planet. It can be larger than the architecture of a solar system. Imagine placing this darkness where the sun sits. The boundary would stretch far beyond the inner planets, reaching into regions where worlds normally spend their lives in stable revolutions. At that scale, something counterintuitive happens to space and time. Near smaller black holes, gravity changes quickly over short distances. The curvature feels steep, like standing on a cliff. But near a horizon this immense, the curvature can appear almost flat locally. An observer drifting near it might not feel an obvious drop-off because the gradient is gentle across human-sized distances. The danger is still absolute. but it does not announce itself with the sharp sensations people expect. This is why TON 618 behaves unlike smaller black holes. Not because the underlying physics is different, but because the scale changes what the physics looks like to anything trying to measure it. The horizon is so vast that classical geometry stops being a reliable intuition. A perfect sphere is easy to picture when the diameter fits into a diagram. But when the boundary is measured in light days, the idea of standing near it and perceiving its shape becomes almost meaningless. The horizon is a global feature of curved space-time, not an object with an outline you can casually observe. So ask the next question carefully. If this darkness is wide enough to swallow the map of a solar system, and gentle enough nearby to feel deceptively normal, what does that do to matter trying to orbit it, to gas trying to feed it, to the quasar that makes it visible across the universe? Because the story is no longer only about mass, it is about scale, and scale changes everything. Black holes were expected to be invisible, not because they are small, and not because they are rare, but because the defining rule sounds absolute. Past the event horizon, light cannot return. The effort for astronomers was learning how to study something that refuses to be seen directly. You look for stars that wobble. You look for gas that accelerates too fast. You look for missing light where something must be eating it. In that older intuition, a black hole is darkness first, and everything else second. Then TON 618 reveals a payoff that feels like a contradiction you can measure. It is classified as a quasar, meaning the region around it is not faint, it is blindingly bright. The black hole itself still does not glow, but the matter feeding it does, and it glows with such intensity that the darkness becomes almost irrelevant. The defining feature, at least to a telescope, is not what disappears, it is what erupts outward before disappearing. The deeper facts are where the brightness becomes a story of physics under stress. As gas and dust spiral inward, they do not fall cleanly. They collide, shear, and churn in a flattened whirlpool called an accretion disk. Friction and compression heat that disk to temperatures so high that the radiation no longer resembles ordinary starlight. Parts of the disk can reach millions of degrees, hot enough to radiate strongly at high energies. That is why the emission stretches across the spectrum, from radio waves to X-rays. It is not one color. It is an entire broadcast. And the scale of the broadcast is the real shock. Estimates place its luminosity at roughly 140 trillion times the luminosity of the Sun, a single object powered not by nuclear fusion, but by gravity converting infalling matter into energy, can outshine whole galaxies. The universe is full of stars, yet here is a system whose brilliance can compete with the combined glow of billions of them. This brightness is not a side detail. It is the reason TON 618 could be found at all. It remains visible across billions of light years because the quasar phase turns a distant black hole into a cosmic lighthouse. Across that distance, individual stars blur into nothing, many galaxies become smudges, but a quasar can cut through the dark like a signal meant to be noticed. So the idea of a black hole as pure invisibility begins to fail. Darkness is not its only identity. With enough mass and enough fuel, the space around the horizon becomes one of the brightest engines nature allows. And that leads to the next question. If this brightness comes from matter falling in, what does the light itself do to the feeding? Can something shine this hard and still keep eating at the rate required to become so massive so early? Scientists map the deep universe the same way they map its past. They take a spectrum, they measure redshift, and they translate that stretch of light into distance and time. It is careful work because the farther the object, the more the universe itself has been changing while the light travelled, and every number becomes a reconstruction. Then the payoff arrives with a quiet shock. TON 618 is seen from roughly 10.4 billion light-years away, meaning its photons have been travelling toward Earth since a time the cosmos barely resembles the one we know. Now, the deeper facts turn the distance into a scene. The light left TON 618 when the universe was only about 3 billion years old, long before Earth existed. The Sun had not formed yet, and the Milky Way was still assembling itself from smaller pieces, still learning how to become a spiral galaxy instead of a chaotic collection of gas and early stars. This is why quasars matter so much in cosmic history. They were more common in the early universe, when galaxies contained richer supplies of cold gas and central black holes had more fuel to swallow. A quasar is not just a bright object. It is a sign that an enormous black hole is actively feeding, converting in falling matter into radiation with terrifying efficiency. And this is where TON 618 tightens the puzzle from the previous parts until it almost snaps. Part 1 asked how a black hole could grow beyond expected limits, and Part 2 showed that its mass rivals or exceeds the stellar mass of many galaxies, and Part 3 revealed a horizon measured in light days, and Part 4 showed brightness so extreme it can be seen across billions of light years. But distance adds a new constraint that is harsher than any comparison. TON 618 was already massive back then. That means the growth had to be extremely rapid because the clock had barely started. Time constraints tighten dramatically, and the familiar slow story of steady feeding begins to sound like the wrong genre entirely. So the question becomes unavoidable. What was the early universe doing differently, and what physics becomes critical when you only have a few billion years to build a black hole that seems to belong to a much older cosmos? The moment we place TON 618 in the early universe, the mystery stops being poetic and becomes mathematical. Physicists did not rely on instinct to understand black hole growth. They built models, turned feeding into equations, and tried to see what the universe permits if you give a black hole gas, time, and gravity. The expectation is simple. A black hole grows by accretion, meaning matter falls inward and adds to its mass. But accretion is not silent. As the material spirals down, it heats up and radiates intensely, and that radiation pushes outward on the very gas trying to fall in. So growth contains its own resistance, like an engine that generates a pressure wave that fights its fuel line. That resistance creates a natural ceiling. At a certain brightness, the outward force of radiation pressure can balance the inward pull of gravity on ionized gas, and that balance point is known as the Eddington limit. In the classical picture, if an accreting black hole tries to shine above that limit, the incoming material should be blown back, throttling the feeding and forcing the system back down. Then comes the payoff, and it is not subtle. The mass estimate for the black hole powering TON 618 is around 66 billion solar masses, and when that number is combined with how early we see it, the usual growth story stops working. Growth beyond the Eddington limited pace is supposed to be impossible for long periods, yet the existence of TON 618 implies a history that looks like it ignored the limit, or found a way around it. Now the deeper facts tighten the trap. Even if you give a black hole continuous maximum growth at the Eddington rate, its mass increases on an exponential timescale known as the salpeter time, often quoted around 45 million years, times a factor that depends on radiative efficiency. That sounds short until you count how many doubling steps are needed to climb from a plausible seed to tens of billions of solar masses, while also remembering that real quasars do not feed perfectly, continuously, forever. Every pause, every shortage of fuel, every burst of feedback makes the schedule worse, not better. So the time available becomes the real enemy. If TON 618 was already enormous, when the universe was only a few billion years old, then continuous maximum growth still struggles, and any realistic duty cycle makes standard models fail outright. And that leaves one unsettling question hanging in the dark. Did TON 618 grow by a process that can exceed the Eddington limit, or did it begin its life already massive enough that the usual starting point is wrong? In the last part, the story narrowed to a single pressure point. If TON 618 was already enormous when the universe was young, then the growth speed problem is not a detail, it is the plot. And the Eddington limit seemed like the final word, the universal rule that turns bright accretion into its own break. The expectation behind that rule is elegant. As matter falls in, the accretion flow radiates. That radiation carries momentum, and when it strikes in flowing gas, it pushes outward. The brighter the flow, the stronger the push, so the system self-regulates. Add more fuel, the object shines harder, and the added resistance slows the inflow until it settles near the limit again. Then comes the payoff, and it is deeply uncomfortable. TON 618 appears to have overcome that regulation. Its existence implies that somehow growth happened in a way that looks sustained and super Eddington, not just a brief flare because the mass is too high for the available time if the limit was obeyed strictly. The deeper facts begin with a subtle loophole. The Eddington limit is derived most cleanly for spherical symmetry, where radiation pushes outward evenly in all directions. But real accretion is not a glowing ball. It is a disk, and a disk has geometry. When gas piles into a thick flow, radiation does not necessarily escape uniformly. Simulations of super Eddington accretion show strong outflows along the rotation axis, while gas can still stream inward near the disk mid-plane, meaning inflow and blowout can coexist in different directions. That is one reason the limit may not apply equally everywhere. If radiation finds an easier exit channel, it can leak out without pushing directly against the densest inflow, weakening the self-regulation that normally shuts the feeding down. In super Eddington regimes, photon trapping and advection can also reduce how efficiently the disk radiates compared to how much mass it swallows, allowing mass inflow to exceed what the luminosity alone would suggest. Then the environment enters the story, and this is where the early universe becomes critical. Models and simulations exploring rapid black hole growth emphasize that exceeding the Eddington rate requires extremely dense surroundings, because the supply must be overwhelming enough to keep pushing inward even while radiation tries to clear it out. If the gas density around the seed was extreme, and if the composition and cooling pathways of early metal-poor gas altered how feedback worked, then the usual braking mechanisms could weaken. Even feedback itself may fail at scale. The same radiation that should regulate growth can also reshape the fuel reservoir, sometimes quenching accretion later, meaning the outcome depends on how gas flows, winds, and feedback couple to the surrounding medium. That makes the physics environment dependent, not because gravity changes, but because the path matter takes through that gravity can change. So the question evolves. If the Eddington limit is not a universal ceiling, but a condition that can be bent by geometry and early universe density, then TON 618 may not be breaking physics at all. It may be revealing the specific circumstances where the universe learned to cheat its own speed limit. After wondering whether geometry and dense early gas could bend the Eddington limit, a deeper doubt quietly appears. Maybe the problem is not only how fast TON 618. Maybe the problem is what it started as. For a long time, the expectation was almost automatic. Black holes begin as the leftovers of stars. A massive star is born, it burns, it collapses, and a small black hole seed remains, ready to grow slowly into something larger. That story feels natural because it uses familiar actors, stars, supernova explosions, and stellar remnants, and it keeps the universe orderly. Then the payoff forces a sharper possibility. Stars may be skipped entirely. The direct collapse idea is not about making a bigger star, it is about never making a star at all. In this scenario, a massive primordial gas cloud collapses almost as a single object, falling inward until it forms a heavy black hole seed directly. No supernova is required because there is no ordinary star that needs to die first. But the deeper facts show why this is so rare and so important. Gas usually cools and fragments. When it cools, it breaks into clumps, and clumps become stars, and the collapse is divided into many small births instead of one enormous fall. Direct collapse requires conditions that keep the gas from fragmenting, often described as minimal cooling, where the cloud stays warm enough to resist breaking apart and instead undergoes a more monolithic collapse. These conditions are not fantasy. Many models place them in the early universe, inside atomic cooling halos, where metal-poor gas and strong radiation backgrounds can suppress molecular hydrogen and reduce the cooling that would otherwise trigger fragmentation. Under such circumstances, theory suggests the seed black hole could be enormous, on the order of 10,000 to 1 million solar masses, far larger than a typical stellar remnant. And suddenly the timeline changes shape. If the seed begins at 10,000 or 100,000 solar masses instead of 10, the required growth time shrinks dramatically. The climb to ultramassive scale still demands extraordinary feeding, but it no longer requires an impossible number of perfect doublings under a strict Eddington ceiling. This is why direct collapse is often invoked to explain how very massive black holes can appear early, powering quasars when the universe was still young. It also fits TON 618 more comfortably than stellar seeds, because it shifts the question from how did it grow so fast to how did it begin so large. Yet even here, the universe refuses to give an easy answer. Direct collapse is still difficult to confirm observationally, because it happens far away, early and quickly, and the signals can resemble other kinds of growing black holes. So the investigation continues, and the next question becomes almost inevitable. If TON 618 needed a head start, what other signs should exist in the early cosmos? Clues that some gas clouds did not become stars at all, but fell straight into darkness. After direct collapse, the mind naturally reaches for an even earlier starting line. If stars can be skipped, then another question follows almost automatically. What if even gas clouds can be skipped? Cosmologists have spent years exploring non-stellar origins, because the universe does not promise that every black hole must be born from a dying star. The effort behind this search is a kind of intellectual honesty. If ordinary seeds grow too slowly, then the origin story itself has to be questioned, even if the alternatives sound extreme. Then comes the payoff, and it is the kind that rewrites the opening chapter. Primordial black holes are hypothetical black holes that could form from density fluctuations in the early universe, before stars and galaxies existed. In this idea, the first seeds would not wait for cosmic structures to assemble. They would appear shortly after the Big Bang, when the universe was hot, dense, and still smoothing out the smallest irregularities. The deeper facts are where the hypothesis becomes both powerful and slippery. If a region of the early universe was slightly denser than its surroundings, gravity could, in principle, overcome pressure and cause that region to collapse directly into a black hole. Because this would happen so early, growth could start extremely early, long before normal astrophysical black holes are even possible. Some models discuss the possibility of massive primordial seeds, large enough to act as gravitational anchors that help matter clump faster than expected, potentially influencing early structure formation. And there is another subtle attraction. If a black hole forms before stars and galaxies, it may bypass some of the usual Eddington constraints at the very beginning, because the environment and the accretion physics in the earliest epochs are not the same as those around mature galaxies. Even without violating any known law, starting earlier changes everything, because the timeline is the enemy in the TON 618 story. This is why primordial black holes are sometimes invoked when astronomers confront anomalous mass distributions, objects that seem too massive too early, or populations that are difficult to build from small stellar remnants alone. But the evidence remains indirect. There is no single observation that forces primordial black holes to exist, and many studies focus on constraints, upper limits, and what the cosmic microwave background and other data allow. So the idea remains theoretical, hovering between mathematical possibility and observational absence. And yet, objects like TON 618 keep it alive, because they keep pressing on the same wound in the standard story. When a black hole appears so massive so early, the universe seems to be hinting that either growth was unusually fast, or the seed was unusually large, or the beginning happened earlier than the familiar script allows. And that sets up the next step in the investigation. If primordial seeds are possible, what fingerprints would they leave behind? And what would it take to tell the difference between an ancient relic from the first moments of time and a black hole that simply learned to grow in an extreme environment? Astronomy is built on a quiet promise. The universe should follow universal rules. The same gravity that guides an orbit in the solar system should also shape a quasar 10 billion light-years away, just expressed at a different scale. That belief is not naivety. It is how science stays coherent. Then TON 618 forces an uncomfortable payoff. Those rules have limits, at least in the way people assumed they could be applied without exception. Not because general relativity suddenly fails, but because the moment a system becomes this extreme, every hidden assumption in the models becomes visible. The deeper facts begin with what TON 618 is in practice. It is a hyperluminous quasar powered by one of the most massive black holes ever estimated, with a mass value commonly cited around 66 billion solar masses. That alone makes it an upper observational boundary, a kind of marker at the edge of what current surveys have been able to identify and measure reliably. And boundaries are not passive, they press back. TON 618 tests general relativity at scale in the sense that its entire behavior, the accretion disk, the radiation, the implied size of the horizon, must still be described by spacetime curvature in the strong gravity regime. The mathematics of relativity has been tested most directly with nearer black holes and compact objects, but objects like TON 618 push attention toward what happens when strong gravity is paired with immense mass and powerful feedback. It also constrains early universe models by existing where it does in cosmic time. High redshift quasars in general already challenge standard formation scenarios because seeds must grow quickly and efficiently, often requiring accretion that exceeds the Eddington rate or very massive initial seeds. TON 618 is one of the most dramatic reminders that black hole growth theory is not just about local physics near the disk, it is about the entire early environment that supplies fuel and shapes feedback. So science is pushed toward possibilities it would rather not need. Unknown or poorly constrained physical processes, sustained super Eddington phases, direct collapse pathways, or other mechanisms that boost growth, start to feel less like exotic options and more like required ingredients. Galaxy evolution models must adjust as well, because a black hole of this scale is not merely living inside a galaxy, it can influence how gas cools, how stars form, and how the host system evolves through feedback. And there is one more implication that is easy to miss. TON 618 suggests larger unseen objects may exist. Detection is biased toward what is bright and active, which means the universe could hide ultramassive black holes that are currently quiet, not accreting strongly, not shining as quasars, and therefore difficult to find. If that is true, then TON 618 is not the ceiling. It is simply the highest point that has been illuminated so far. In that sense, TON 618 becomes a boundary marker of knowledge. It tells science where confidence ends and where the next set of rules must be tested, revised, or expanded, not in a different universe, but in this one.